Solutions, as the subtitle implies, this is important. The majority of the chemistry we do, and we didn't do a lot of this when we were doing reactions, we didn't do the calculation side of this, but a lot of what we do is solution chemistry. Ionic compounds are oftentimes going to be aqueous solutions in both single displacement and double displacement reactions. And so it's important that we understand what solutions are, how they work, how we do concentration. So a solution has essentially two parts, and it is a homogeneous mixture. That when we say solution, we mean that it is uniform throughout, that there's not stuff on the bottom, that it's not, some type of other thing. And so when we talk about solution, we mean homogeneous mixture. Always has two parts: the solvent, the part that does the dissolving, and then the solute, the part that is dissolved. Now, in certain types of solutions, you can't really say there's dissolving going on. And so we will say, hey, the highest mole fraction is the solvent, the lower mole fraction is the solute. And you can have more than one solute in a mixture, okay, or in a solution. So, for example, just looking at the different types, you can have a gas and a gas, like air. In air, like we said, it's nitrogen, it's oxygen, water vapor, carbon dioxide, argon, and other gases. The solvent is the nitrogen because it is the highest mole fraction, and then everything else is solute. So oxygen's a solute, carbon dioxide's a solute, water vapor is a solute, argon's a solute. All those are solutes in the solvent of nitrogen when we're talking about air. We can also do gases into a liquid. Carbonation is a good example. Carbonation is carbon dioxide dissolved in water. Now, when it dissolves in water, it forms carbonic acid, but it's still a process of dissolving carbon dioxide into water. We can have a liquid in a liquid, like, for example, vinegar. If you look at a bottle of vinegar, it'll say, and I'm trying to remember what the percents are off the top of my head, 5% acid by volume or something like that. And that means that it's 5% acetic acid and 95% water. There is such a thing as glacial acetic acid, which is pure acetic acid, 100%. It smells kind of like vinegar, but a lot stronger. Then we can have a solid in a liquid, salt water, sugar water, any of those solids that we dissolve in water. We can also have a solid in a solid. That we look at 14 karat gold. It's a mixture of gold and silver. 24 karat gold, your pure gold. However, 24 karat gold is way too soft for most uses. And so it is generally mixed with some other metals to bring it down to 14 karat. And so the gold is the solvent in this case, and in 14 karat. And then like the silver would be your solute. And that's alloys can kind of work that way in terms of, because they are solutions. All right, so when we're talking about solutions, we need to talk about solubility. And solubility is the ability of something to be dissolved, or the ability for it to mix in. Think about it like, if you're making something with sugar and water, like sweet tea or Kool-Aid or something like that, you get to a point where you can't get any more sugar in it, and it's no longer soluble. It just settles to the bottom. And so that's what we mean by solubility. Also with solubility, is related to that is miscibility, which means that things can be mixed. So, for example, oil and vinegar or oil and water are not soluble with each other. They're not miscible. You can't mix them together. They're always going to separate into two layers. So the first factor that affects solubility, temperature. Increasing temperature generally tends to increase solubility of liquids and solids. Think about it. Hot water will hold more sugar in it than cold water. If you live in the South and you make sweet tea, you understand this concept. All right. It leads to a decrease in solubility for gases, though. Think ice cold Coke. You open that can, you open that bottle, there's not going to be a whole lot of fizz because it's ice cold. Most of that's going to stay in. Those bubbles, that carbonation is staying soluble in the water. But you open a warm one that's been outside on a warm day, and all of a sudden it's going to fizz a lot. And that's because the solubility is decreased because of the temperature. All right, pressure. This is what specifically has the greatest effect on gases. For example, your container doesn't fizz. You look at a 2-liter bottle of Coke, It's not going to fizz as long as the container is closed. It's under pressure. And as soon as you open it, you hear the psss. It's releasing pressure, and all of a sudden its solubility decreases. It starts fizzing. And so increase the pressure, you increase the solubility for gases. All right, so not only do we need to see whether or not things dissolve and maybe help them dissolve, what also comes into play is how fast things dissolve, or the rate of dissolution. There are 3 factors that can make things dissolve faster. First of all, temperature. Generally speaking, once again, this would be solids and liquids dissolved into a liquid or another solid. Temperature is going to make this easier. That the hotter the water, the faster the sugar will dissolve, or the faster the salt will dissolve, whatever. Stirring. If you ever tried to make Kool-Aid or sweet tea or something like that, you understand this. If I stir it and I mix it, I'm getting more agitation in there. I'm getting more solute-solvent contact, and it's going to dissolve faster. And the last one is surface area. Back in the old days, they used to use lumps of sugar, or cubes of sugar. Well, when you put a cube of sugar into a cup of tea or anything else like that, coffee, only so much can dissolve, because only the outer surface is touching the liquid. Where if you take granulated sugar and you add that in, every side of every piece of sugar is touching the liquid, and therefore it dissolves significantly faster. And so that's the kind of making solutions. And so now we're going to talk about how we describe a solution. And one of the most important ways of describing a solution is its concentration. Concentration basically tells you how much stuff is in it, how much stuff has been dissolved. Now, there are several ways to talk about this, and the major ways we talk about it in chemistry are going to be molarity, molality, and mole fraction. As the names imply, they're all related to moles. The number one that you will see, and the number one that we're going to talk about in this class, is this, molarity, which is moles per liter. So if I have a certain number of moles of salt, NaCl, so I have 5 moles of sodium chloride in 1 liter of water, it would be it would have a molarity of 5. It would have 5 moles of salt per 1 liter of solution. And we would say it's 5 molar. Okay, so when we're describing this, we say molar. So 5 molar solution, a 1 molar solution, something along those lines. Molality is used when we're dissolving. Generally, it's really helpful when you're doing a solid into another solid, if we're talking about kilograms. So we're talking about solute per kilogram. And when we're talking about liquids, we don't generally talk about kilograms. We talk about liters. But when we're talking about solids, this is what we want to use. And so you can talk about molality that way. And when we're talking about gases, mole fractions is easier. And so we generally tend to use mole fractions when discussing the concentration of gases. And so it depends what you're talking about as to which unit you use. Like I said, in chemistry, the most common is aqueous solutions, an ionic compound dissolved in water. And that's why we will use molarity, because we're dissolving into liters of water or liters of solution. All right. Other common ways, percent mass and percent volume. When you see hydrogen peroxide, vinegar, you'll see it on other things that you see, just household items. It'll say so and such percent. And usually that's going to be a percent mass or a percent volume. They are not really good as to saying which one it is. Usually it's mass, but that does happen. So if you're talking about solids, it's going to be percent mass. If you're talking about liquids, it's probably percent volume. Another way that I don't have listed here that is a common way of discussing concentration is saturated, unsaturated, and supersaturated. So a saturated solution means something's holding as much as it can. Unsaturated means it's holding less than it can. And then supersaturated means it's holding more than it can. Now, people wonder, well, how can you make something that's supersaturated? How can you make something that has more than it's supposed to? Well, remember, solubility is related to temperature. So let's say this is the amount of, just imagine there's a line here, that this is the amount of sugar that room temperature water can hold. Well, if you live in the South and you want to make sweet tea, you don't want this much sugar. You want more sugar. And so what you do is you heat it up until it can hold this much sugar. And you dump all that sugar in, and then you cool it back down to room temperature, and now that extra sugar is going to stay dissolved in the water. And that creates what is called a supersaturated solution. So you heat something up, dump your solute in, and then cool it back down, you create what's called a supersaturated solution. Right, let's actually look at doing molarity, because like I said, it's the most important one that we're going to be using in chemistry. So given the amount of solute in a volume, so if you have 50 grams of table salt and 1.25 liters of a solution, find the molarity. Well, molarity is defined as moles per liter. So I need to convert that grams to moles because I need to be in moles. So convert the grams to moles. That should be pretty common sense by now, hopefully. So use a molar mass, convert it to moles, and then you simply take your moles, divided by your liters, and you get your molarity. 0.684 molar NaCl, or you would say that it has a molarity of 0.684. You could say it that way. Now, that's one way that we do these, and that's more common when you're given an amount that you're starting with. But another one that's fairly common is if you're given the concentration and the volume. When you're doing an experiment, you're said to get this many milliliters of this solution, but you need to know how many moles you're reacting with. And so first thing we got to do is remember, molarity is moles per liter. This is milliliters. Not very helpful. So convert milliliters to liters, and that'll give me what I need. And then if this is moles per liter, and this is liters, if I multiply them by each other, then I get moles, because the liters will cancel out. So this is moles, and this is moles per liter. The liters will cancel out. And then I get this. Okay? And that's how many moles I had that I used in my reaction. So that's a very common way of doing that. So there will be some more molarity calculation questions in your workbook. So give those a try, and I will see you in the next lesson.